Hey, sir, I actually had a question for you.
No problem. Go for it.
I so on our module one,
Mm-hmm.
it had the three homework assignments. So it was like the syllabus, the mastering physics, and then the physics primer.
Mm-hmm.
And then
Should have chapter
I
one
didn't, there was
concept and
also,
chapter one homework too.
yeah, but it wasn't in the module. So I couldn't see it. And it's fine. I'm not trying to make it up, but I'm just asking if you could post the chapter two homework and conceptual in the module so that it pops up for me.
Yeah, it was supposed to be in the module. I did notice that week two did not have it in there. I'm gonna go ahead just because of that. I'm gonna go ahead and make. Oh yeah, it's definitely not in there. That's weird. I don't know how it ended up not in there. Okay, I'm gonna put that in there and I'm gonna extend the deadline till this Sunday.
Okay. All right.
Okay,
I
just
appreciate it.
yeah,
Thank you.
it's not cool that I didn't put it there. Sorry about that, bud.
It's okay.
Yeah, they're supposed to be there every week, everybody. Thanks for letting me know. I'm gonna go ahead and set the date a little further back, just to give y'all credit for this. So let me go to my Pearson and change the date on that. Anybody else have any question? Feel free to ask. Thank you for going. I see that you went ahead and chatted me your first and last name. Appreciate that. So chapter one was due 8/31. I'm gonna now do make that due 9/7, and both of those are set now. That should be good. Yeah, if y'all ever see me leaving those off, by all means, send me a text just to remind me. But yeah, they're supposed to be there every time. I don't know how that one got mixed up. It must have been because I was, flipping back and forth between three different pages and just left it off this particular one. So, anyways, it's up there now. And I did log in early. I logged in about 12 minutes early, just in case anybody had any questions. So I want to make sure y'all have a chance to ask questions even before class starts.
Yeah, I had a question about wait, can you hear me?
I do hear you, Taylor.
Okay, my mic thing wasn't popping up, so I didn't know if it was working.
Okay.
Sorry.
Yeah, no
Um,
problem.
the Archimedes bathtub question was in one of the homeworks. Is there no way to figure that out if the question doesn't give it to you, if you don't look up the specific dimensions of the bathtub and you do that research? That's a question that we had to look a lot of stuff up for, correct?
Yeah, you shouldn't need the dimensions of the bathtub, but I gotta look at that question again. This was chapter one. Was it conceptual or
No, it was
homework?
the normal.
Okay, let me look at it real quick and see what it says. I
It
just
was
finished.
asking how many would be in your everyday soda can, so I had to look up the
I
averages for
gotcha.
those to figure it out. I mean, I
Uh,
figured it out. I just wanted to make sure if there was a question like that on a test, if we could still look it up.
say if it was on a test. I wouldn't need to give you information, or you asked me for it, and if you asked me for it and I didn't deem that you needed it, then I wouldn't give it to you. So that's the way that would work out. But to be
Okay.
honest with you, normally the testing is a lot lower level in most cases than the actual homeworks. The homeworks are preparing you to do a lot of stuff, and then I try to test on a little bit more moderate things. So it, such a question just probably would not appear as a test question, put it that way.
Okay. Thank you.
But always ask if you have something that you don't understand and you're not sure that you need to know it. Ask me or ask whoever your instructor is, and they should be able to allow you, tell you that you can have it and give it to you, or tell you that you can't have it.
Okay. Thanks.
No problem. Got another student came in. This is from one. That did not pop up. Let's try 1-9. Hmm. Yeah, I'm not finding that question. I sort of remember it, but I'm not seeing it now. Hmm. Not there. Not there either. It's still not there. This one either. Ah, there it is. Okay, it's that one. So at least I did find that question. It's evidently the made to order of magnitude or something. We've still got about 5 minutes, so feel free to ask me any questions you might have. That's why I'm here early. Of course, I'll still try to open up the floor to questions when class, excuse me, when class starts. But this should knock some of that out if possible. I'm pretty certain that sounds horrible to you guys. I apologize. I got the microphone right here and I'm taking a sip of drink and it probably sounds like a pig or something. Students have already begun chatting me their first and last name, so feel free to do that. I also want to remind you guys you need to let me know if y'all have any issues with your name and or occasionally your face appearing on the internet. Uh, I want to make sure you guys know that that's something that happens because I automatically record these and I very rarely even do any editing first and then I just post them straight to my YouTube channel. So, if anybody's in witness protection or something, you might need to let me know and you might want to go ahead and change your username in Zoom to something a little less serious, like just, maybe your initials, but with a random name on it or something like that, just to conceal your identity. But when you actually chat me your first and last name for the attendance, then I'll see what your real name is. Plus, I can also tell from some other stuff that Zoom provides me. But the main thing is, like I said, if you don't want your name or image to appear on YouTube, my YouTube channel, you need to let me know by email, and I'll do my best to make sure I cut all that out and that sort of stuff. Still got about
Um,
3 minutes. Go ahead.
since the homework due on Sunday isn't based on a chapter, where do we find the material to look over for that?
The homework due on Sunday. What exactly homework are you referring to on that?
It
You talking about the
says,
physics primer or intro to
yeah, the
mastering?
the Introduction to Mastering Physics primer.
Yeah, they're just supposed to be teaching you specifically how to use the website. So
Okay,
you don't need any additional stuff. They show you how to enter stuff, that sort of thing.
thank you.
No problem. You're welcome. Anybody else? Still got a couple minutes. If you have a problem remotely, you need to let me know via email. So if someone has a potential problem that prevents them from getting to a proctor, one of our proctor campus testing centers or my personal classrooms, and you need some other way, then yeah, you need to email me, let me know exactly what the problem is, or you can text message me and let me know exactly what the problem is. But remember, when you email me or text message me, I want you to include your first and last name and what class you're in. And of course, if you're emailing me, you're supposed to start the subject line with the class number. And you're still supposed to put your first and last name in it, and you're only supposed to use your TCC email account. So, all right. We got about 1 minute left. Looks like most people are going ahead and chatting your first and last name in. That should be done, so please do. Uh, y- Ian, you're asking about did you miss the extra credit? You can still turn it in if that's what you're asking. I was wondering if you're asking, is it not there or something? Oh yeah, don't worry about the due date. If I don't take something late, then it'll have like a cutoff date and like when you're past that date, it won't let you submit anything. Whereas if I'm allowing you to turn it in late, there's going to be possibly points taken off for it being late, not necessarily an extra credit, but it would be points let off and it'd still let you turn it in early. I mean, it still lets you turn it in late. But if I absolutely said no, you can't turn something in late, then it would literally not take it from you. So by all means, yes, submit it. And a lot of times when I go to do stuff like that, if I grade it after you submitted it, I don't even mark it as late. I try to do that just because sometimes I get behind in my own grading, so it's only fair that if you get a little behind and it doesn't hold me up, then I'm not going to take off points for you doing that. So still try to get all your stuff in on time, but just know that I'm careful and I try not to be unfair. All right. Well, it's definitely 6:31, so we want to get started. I want to remind everybody that this first part is normally for you to ask me questions if you have any. I actually been trying to log in early so that we can get some of those questions out, and I've already answered some questions. But because people can't necessarily get here early, that means I still open up the first beginning of class to anybody asking me a question. So by all means, ask me questions. The other thing is, I want to remind you that you need to email me and let me know if you have any problems with your name or image or face or anything appearing on my YouTube channel. Like I said, you might be in protective custody or something. You might be hiding from a scary spouse or something like that, just let me know. The main thing is I want to protect all my students. So if you have a problem with it, you need to let me know so I can make sure I do it. I would also recommend if you don't want your name at all being exposed, then you need to change your Zoom username to something like maybe your first initial and your last name's first initial, and then just some random name at the end because I can always cross-reference it and figure out exactly who you are. Not only that, you're going to chat your first and last name at some time in each class for your attendance. So now go ahead and chat me your first and last name if you haven't done so already. Again, let me know by email if you can't have your image or your name on the internet. And I'm opening the floor to any questions people might have on homework or anything else for that matter.
Hey, I have a question.
Go for it.
So I recently just joined this class. Do
Mhm.
I have like extended dates for homework that was due previously?
We're not supposed to, but I do. Okay, so they normally tell us that whatever days you miss, those are just the days you miss. So in that part, like if you have me for lab, which you probably don't, then you would actually lose the attendance points for those days. But in my class, if you tell me when you get, for instance, we've done chapter one already, and we're starting into chapter two, and you're just here today. So when you finish chapter one and chapter two, if you let me know, I'll go back and you just remind me of this conversation, and I'll go back and erase the late points for those two assignments, but only those two assignments. Okay? It's
Okay.
going to mark you as a penalty for being late, but I'm going to go and erase those when you're done. So just let me know. And at the same time, you need to keep up. So like if we start chapter three, you want to make sure you meet the deadline on chapter three. Not You're not getting an extension on that one. Okay.
All right.
Anybody else have any questions? So yeah, I try to be nice to you guys on that sort of stuff. I don't want to, punish anybody for any. I don't want to punish any of you for anything. I just want you all to do really well, learn a lot of stuff, and everybody get A's, and I'll be happy and you be happy. So give that a try. It looks like we've answered all the questions. I've got a person here writing. I read Ian's already. Just joined class and I'm having trouble accessing the work through Pearson. It asks for an access code. Okay, so the access code, there's an access code that you get by purchasing a new book, or you can get it by purchasing a used book at some stores. Uh, but you can also get it by just going into Canvas and go into my class, click on homework assignment one. Usually that works. Sometimes it doesn't. If it doesn't, go to the left-hand side of Canvas and it says Access Pearson. You're going to click on that. And at that point, it'll give you a chance to either enter an access code, which is what you'd get if you bought it from the student store or some other store, or you can take a 2 week free trial period. So you can do that, or you can purchase it right there. That is the cheapest way to purchase that access is right there, and you'd want to purchase it with the ebook as well. Uh, I would also not recommend you doing short weeks because sometimes they'll have like, oh, this is the 18-week pass, which if you're not taking the second semester, that might sound pretty good, but a lot of times students don't pass the first semester and then you have to buy it again. So if that's even remotely a possibility that you might not pass, it might be better to just pay for the full access that lasts, the life of the edition. So do that. If you have any problems, then you might want to call Pearson. But other than that, you want to make sure you only go through Canvas. So never try to go to mastering from the internet. You want to go to Canvas first and then go to mastering through Canvas. If you find a way to do it another way, you're going to ruin yourself and it's going to make it where I can't access your grades. So don't do that. You might be able to. They might actually give you a refund and make it a 20, whatever the full one is. For this is Ryan that asked me, can we upgrade from 18 weeks to full? So yes, you will, assuming you're taking both semesters here or both semesters somewhere where the same book is used, then you can use it next semester as well. So yeah, I would maybe contact Pearson or maybe even contact the bookstore, but I think it'd probably be more likely that you'd have to interact with Pearson to find out if you can upgrade it from 18-week to the other option. Anybody else? All right. Well, last time we finished chapter one, and now we're in chapter two. So, what I'm going to do is I'm going to be talking about chapter two, and it really would be best if you had your e-text open to chapter two, because what I'm going to be doing is working examples from the book, and I'm not taking the time to write out or type out the examples from the book. I'm going to read them to you, but it's not going to give you enough time to actually write down those examples. So if you need to re-look at it or something, you can ask me and I will repeat whatever I said. But the main thing is if you want to read it, it'd be best that you had it open. So do have your e-text open. The chapter we're doing is chapter two, describing motion, kinematics in one dimension. And as always, I told you there is a chapter opening question that you should, in fact, answer every time. This is sort of like John Wheeler said, never solve a physics problem whose answer you don't already know. This is you actually taking a poke at what that answer should be so that you'll have an answer. And then later on in the textbook, you're going to learn some amount of physics that allows you to get the right answer to that. And at that time, you'll be solving a physics problem whose answer you quote unquote already knew. In other words, you already had an answer you hypothesized, and now looking at the material and learning it, you can check your logic and figure out, what you did wrong if you didn't get the right answer, or you can pat yourself on the back for getting the right answer, both of which are really good to the learning process. So please, please, please do that. I will tell you the sections from chapter two are section one, reference frames and displacement. Section two is average velocity. Section three is instantaneous velocity. Section four is acceleration. Five is motion at constant acceleration. Six is solving problems. Seven is free falling objects. and 8 is variable acceleration integral calculus. We will be covering all of those, and in fact, section 8 is something that I do every semester to make sure my students really understand how to go through the process of taking definitions, specifically the definition of acceleration, and using calculus to figure out the velocity as a function of time, if you know the acceleration as a function of time, and then, of course, with initial conditions, and then using that velocity as a function of time with initial conditions to figure out the position as a function of time. It's basically the same process as I go through in deriving the kinematic equations, only it's for a case where the acceleration is not a constant. So I will be showing you that as well. Uh, we're going to start off by talking about reference frames. And what I mean by that is whenever you state something like, hey, this person's at 3 meters, when you say this person's at 3 meters, that you're not giving enough information unless you've already started some kind of lab environment with the people that you're talking to, and you've already got some kind of language established. No one knows what you're talking about. But if you have, already started a lab and worked this out, that's a very common thing to say is I'm at 3 meters, right? But in general, if there's any ambiguity, you need to specify at 3 meters with respect to what, and that's the wording that we often use is with respect to. So when someone tells you they're driving 60 miles per hour, that's pretty usually unambiguous. That means you're traveling at 60 miles per hour relative to the Earth. But sometimes it's not that obvious. For instance, you might be talking about the velocity of a ball that you're throwing from the bed of a flatbed truck. In which case, the velocity of the ball relative to the flatbed truck is one thing, and that's probably the thing you're going to talk about. But then there's also a velocity of the ball with respect to the Earth. And then there also might be, depending on what kind of problem they set up, the velocity of the ball with respect to the moon, or the velocity of the ball with respect to Saturn, or something crazy like that. All of those are real options. So it's important for you to understand that in general, the way we uh, say with respect to is we imagine a coordinate system. So we always imagine a coordinate system, or I should say always. I shouldn't say always. Occasionally, there's ways you can do physics without coordinate systems, but in general, especially early on, the vast majority of stuff you have to do uh, may be made a lot easier by drawing a coordinate system. And normally the coordinate system is X goes left and right, Y goes up and down. But if you move to 3 dimensions, then it's sometimes X is out and in, Y is left and right, and then Z is up and down. Uh, the main thing is when you're dealing with a coordinate system, it needs to be right-handed. So that means if you hold your right hand like this, notice I've got my thumb being perpendicular to my index finger, and I've got my middle finger being perpendicular to my index finger, and I've got my middle finger perpendicular to my thumb. So they're all three mutually perpendicular. This is my right hand, and what I mean by my coordinate system being right-handed, you should be able to lay this finger pointing in the positive X direction, and then orient your hand so that this finger points in the positive Y direction. And then if you have that, then automatically the Z will point in the direction of my thumb. If you have a left-handed coordinate system, you can still do physics, but it's going to be complicated, like formulas like you'll use for determinants and stuff like that just turn out to be wrong. Like they're going to be off by a negative sign, and it's just a pain to track down. So it's just better to ignore all that BS and just jump right to a right-handed coordinate system. So in this chapter, we're talking specifically about kinematics in one dimension. Specifically, the chapter is called Describing Motion Kinematics in One Dimension. And I'll tell you that kinematics specifically just means the study of motion without wondering exactly how you make the motion occur. So let's say a particular particle has a particular mass, it has a particular velocity, a particular acceleration. At one particular point in time, and it has a very particular initial position. With that information, the mass, might not even need the mass, but the initial position, the initial velocity, and the initial acceleration are the acceleration as an actual function, or the position as a function, or the velocity as a function. With that kind of information, you should be able to predict what the position, velocity, and acceleration are at any point later without really understanding what was done to cause the acceleration or what was done to cause the velocity. That's kinematics. Now, in this case, we're limiting it to one dimension, and what we mean by that is one way of thinking about it is a number line. So we know, x-axis, y-axis, but if you're talking about one dimension, just throw away the y-axis and you just got an x-axis, which is a number line, right? And a number line has an origin, that's where the zero is, and one direction, either to the right or to the left, is going to be a positive direction, and by default the other one has to be negative. And once you have that, then you have a coordinate system. Now, that could be actually on a number line, but this also could represent little marks on a wire, say a wire that's not straight. It might be a helical wire or something like that, but it's still one-dimensional motion because you can identify the position by one number, specifically its x position, because somewhere on that helical wire you've made a little etching to show where the zero is, and you show that going one direction from that zero is the positive direction, going the other direction from that zero is the negative direction, and therefore you still only need one coordinate to define it, even though the path is quite different from straight. Now, it might be a little more complicated to solve it, but the fact is you can. So, just to give you an idea, when you actually start talking about motion in one dimension, we're going to come up with things like position, distance traveled, a weird thing called displacement. You're going to introduce something called speed and something else called velocity, which are normally very interchangeable in everyday life, but in this case, they're going to be quite different. So let me start off with just an idea of what we mean by a reference frame. So, for instance, I'm going to go ahead and share my screen with you now. Let's hope all this works out nicely. And remember, try to have your ebook open. That would be helpful so that I can work the examples in the book and uh, not have to show it on the screen. I will read them, of course, but I'm just not going to take the time to write them or type them out or anything. Okay, so you're all looking at the screen. So what we might imagine, for instance, is a Mack truck. And your Mack truck might look something like this. And then the Mack truck might have a flatbed trailer on the back. And there might be a person standing here. And in fact, you might say that the velocity of the truck, and when I say this, when I tell you the velocity of the truck is like 60 miles per hour, everybody understands that you're probably meaning the velocity of the truck with respect to Earth. And the way we indicate that is VTE. And I'm saying velocity because it turns out that velocity is ultimately going to be a vector quantity. And I'll explain what that is in a second, but that's what I'm using right now. And the subscript T is the object whose velocity I'm talking about. And the subscript E, the second subscript, is the reference frame or the object I'm measuring it with respect to. So I'm going to say the velocity of the truck with respect to the Earth is positive 60 miles per hour. From this diagram, we can see the arrow shows it moving to the right. Therefore, it's obvious that I have chosen to call the right direction the positive direction, right? Now, if this person on the flatbed truck throws a ball in the same direction the truck is driving, then you might say the velocity of the ball with respect to the truck is equal to positive 50 miles per hour. I'm going to treat both of these things as if they're two sig figs exactly, so there's no ambiguity in the zero digit, the ones digit that I'm using on these two numbers. Now, you can see in this case that I'm talking about the velocity of the truck as seen by the Earth means I'm measuring the velocity of the truck relative to the Earth. Similarly, the velocity of the ball with respect to the truck means I'm measuring it with respect to the trailer of the truck or the truck itself. Now, in order for you to have some understanding of how this stuff works, there should be some kind of addition of velocities or relative velocity formula, and I'm going to give you a formula for that. And it's one that they hint at a little bit in this chapter, but they mostly cover it in chapter 3. But I'm going to go ahead and knock it out, and I'm going to give you an idea of how it changes in relativity, because this is my one chance to talk about relativity, even if we don't get far enough along at the end of the semester so that I can cover relativity. So here's the rule for velocity addition, and this is actually true in 2 dimensions, 3 dimensions, and therefore I'm going to write it as a vector equation. Again, if you don't know what a vector is, don't worry about it. Just know that when I say something is a vector, then I usually write the symbol with a little arrow over top of it. So the addition of velocities, or the relative velocity formula, is the velocity of A as seen by C. Now it is velocity, so I'll put that arrow over it. The velocity of object A relative to C is equal to, now pay attention to how I do this. It's the velocity of A as seen by something, but I don't know what that something is yet, so I'm leaving a space, plus the velocity of something. Again, I don't know what that is either, so I'm leaving a space, but it has to be with respect to C. So notice how the A, which is the first subscript, matches the first subscript of the symbol, of the first symbol in the addition formula. Similarly, notice how the second subscript is the second subscript on the second quantity. That's what has to be true. Okay. Now, the other part of this equation that has to be true in order for the equation to work is that the two inner subscripts have to match each other. So, for instance, I could put a B right here, and then that causes this to be a B. So, in this case, you're going to say the inner subscripts have to match. Now, as long as you write it like that, such that AC, which is the left-hand side, is matched by the first subscript of the first term and the last subscript of the last term, then you'll automatically have the right formula as long as the two middle subscripts are equal. In other words, B and B. Okay? Now, in addition to that, it turns out really handy if you know another principle, and I'm going to tell you that now. In order for you to best understand it, though, I want you to think about riding in a car. Let's say you're riding in a car in a passenger seat in a weird car where you can actually turn the seat so it turns 90 degrees to the path you're traveling in, so that you don't have to look straight forward or straight backwards. You can look actually straight out the side. So if you're, say, in the left-hand lane of an interstate and someone else is in the right-hand lane of the interstate right next to you, if y'all are going the same speed, then you would look over at this person to the right of you and you'd see them not moving with respect to you. And that's how you'd know you're going the same speed. But if all of a sudden you see this vehicle coming from your far right hand side, remember you're sitting sideways, the vehicle's going this way like this. If you see a car coming from your right hand side going off to your left hand side, or you could do it the other way around, in which case the car is coming from the left going to the right. Doesn't matter, but whichever way you do, you're going to choose one direction as positive and the opposite direction has to be negative. So right now I'm seeing a vehicle coming from my right going to my left, and I quickly do a video of it on my phone, and I use some quick software, and I determine that the vehicle is moving with respect to me at 10 miles per hour. Okay. If I'm going 60, then we know that means this vehicle must be going 70. But the big deal is it's going from right to left, and I'm calling left the positive direction. So my idea is the velocity of the other car, V0 or VO, because it's O for other, with respect to me. So VOM is equal to positive 10 miles per hour. Now imagine someone in that car, they would have to sit with their seat turned this way, but they'd have to agree with me on what the positive direction is. So the fact that I said the direction was that way is positive means they got to say that direction is still positive. So to them, what they're seeing is my car going from forward and to the right going past us to the left. Okay? So they would automatically say that the velocity of me with respect to the other, that means with respect to them, is equal to negative 10 miles per hour. That's not a happenstance that you get the same number but with a different side. And the way we tell you that is that the velocity of A with respect to B is equal to the negative of the velocity of B with respect to A. You're going to find out that this turns out to be the same thing as or a similar formula as Newton's third law. For every action, there's equal but opposite reaction. But it has to be true. As you saw, the velocity of A with respect to B must be the velocity of B with respect to A times negative 1. Okay, so that comes in handy. Now, if we want to talk about the velocity of the ball with respect to Earth, because notice we're referring back to the person standing on the flatbed Mack truck and the truck moving 60 miles per hour in the positive direction to the right, and the person throwing a ball in the positive direction, i.e., to the right at 50 miles per hour. We want to know what the velocity of the ball will be with respect to Earth. Sorry, I keep yawning. Again, I can put vectors on here, and it is a true vector equation, but in this case, we're doing one dimension, so the vectorness of it is literally just handled by a positive sign indicates the vector points to the right in this particular example, and a negative sign indicates the vector points to the left. So VBE, I'm going to apply my rule that I taught you. I want the velocity of B with respect to E, so that means the velocity in the first term is going to have a subscript B as its first subscript, and the second term, its second subscript is going to have to be E. Now all I need to do is make sure the innermost subscripts match each other. What I do have is a VBT, so it compels me to go ahead and put T there. So I'm going to say the velocity of B with respect to T plus the velocity of T with respect to E. Okay, so that actually works. And again, I could put the vector arrows over top of all these because it is a true vector equation that would work. But in this case, I just don't need it. So now I know that the velocity of the ball with respect to the truck is positive 50 miles per hour. And I know that the velocity of the truck with respect to the Earth is positive 60 miles per hour. Again, these are not the units we normally use in a physics class, but I'm trying to make sure it's as simple as possible. So I want it to be something that you experience more often. And of course, the answer here is 110 miles per hour in the positive direction. That is what we call Galilean relativity or Galilean relative motion. Okay. Relativity in terms of Einstein's special theory of relativity is quite a bit different, and I'm going to show you that now. But notice this formula does work. The velocity of A as seen by C is equal to the velocity of A as seen by B plus the velocity of B as seen by C. And you can always use, if you need to, the velocity of A with respect to B is equal to the negative of the velocity of B with respect to A. Let me show you exactly how that works. Again, this is a relativistic problem, and there is a possibility that you could have a relativistic problem. So pay close enough attention to be able to answer such a question, but know that it's not that critical to the course right now unless we happen to get far enough where I can cover relativity. So
You said this was Galilean what again?
Galilean relativity,
Thank you.
no problem. You could also call it classical relativity or something like that. Anytime you're talking about relative motion, it's a version of relativity. In this case, it was Galilean. Now, the difference is when I say the velocity of A as seen by C, in relativity, special relativity, I can't call this a vector equation because it's a little bit more complicated if you're talking about motion that's not in one dimension. So just remember that this is only an addition of velocities type formula for one dimension, but it looks very much similar or excuse me, I wrote plus there instead of equals. It's still going to be the velocity of A as seen by B plus the velocity of B as seen by C. But it's got this extra part in the bottom that, of course, if you ever take relativity, that's one of the first things you work out for yourself is to figure out how velocities add, and you'd get this result. But this is the result. Notice it looks the same as the other one, but it has this bottom denominator that's quite a bit different, and that c right there is the speed of light. And the speed of light c is 299,792,458 meters per second. And that's it to an infinite number of decimal places. In other words, the 8 is followed by a decimal, and then an infinite number of zeros because we've defined it to be such. Okay. That's also about 186,000 miles per second. It's just to give you an idea how big that is. So you can imagine if you really wanted to know it in miles per hour, it's going to be 3,600 times bigger than 186,000. So if you multiplied 186,000 times 3,600, you'd get the actual speed of light in miles per hour. That's a big number. It's so big, mind you, that it can get basically light can bounce off the sun and, or excuse me, bounce off the moon and hit us within a little bit over a second. It can go 8 times around our equator in a single second. So if you could compel light to go in a circle following our equator, it would make it around our equator 8 times in a single second. So it's a really, really big velocity. Now, let me show you.
And
Go ahead.
when using this equation, we have to take that number and square it before
Yeah,
dividing with it.
yeah, exactly. That's crazy, ain't it? But I'll show you that normally we work it in such a way that it works out really easily. So I'm going to show you an example right now. Let's imagine, for instance, that we have the Earth right here. And what I have is a spacecraft right here, spacecraft A. And spacecraft A has a velocity AE, that's the velocity of A with respect to the Earth. I'm going to separate this so it won't get too messy. But the velocity of spacecraft A with respect to Earth is going to be positive, I'm going to say 9/10 c. Notice how I'm writing it as a fraction of c or a multiple of c. In doing that, I can save myself the problem of trying to square a c. Okay, so yeah, it would be kind of ugly otherwise. Now let's imagine there's another spacecraft B right here, and it's moving with a velocity of, let's say the velocity, whoa, Dilly, I don't know what happened there. I must have changed my pencil writing all of a sudden. But this is going to be the velocity of B as seen by E is equal to, notice it's going in the left direction. And everybody, when you're using these equations, everybody has to agree what direction is positive X, what direction is positive Y, what direction is positive Z. So in this case, I'm going to say the velocity of B with respect to E is 7/8 C, but it's negative because it's going to the left. Okay. So what I'd like to know is the velocity of A as seen by B. Now, this is a typical problem. Like if you were on a highway driving 35 miles per hour north and another car was driving on that same highway, but they're headed south at 35 miles per hour, then you know the velocity with which the car is coming towards you is 35 plus 35 or 70 miles per hour. This is sort of that same thing. I'm trying to say, how quickly is A getting to me as a person on ship B? So according to our rule, velocity of A as seen by B has got to be the velocity of A as seen by something plus the velocity of something as seen by B. Well, I do have VAE, so I'm going to put E there, and that forces me to have VEB for the second one. Notice I have VBE, but I don't have VEB. So that's why I get to use that other little rule right here, and I use it as follows. Oh, by the way, I forgot the denominator. 1 plus VAE VEB over C squared. So what I can do is I can say this is the same thing as velocity A with respect to E minus the velocity of B with respect to E divided by 1 minus, notice I'm flipping out the VEB. I'm replacing that with VEB and a negative sign. So that's why the two negatives appeared. Now I have VAE, VBE, all that over C squared. And when I go ahead and add these two, actually, you know what? Yeah, I'll do it. It's fine. I used different numbers earlier. I was going to use the same numbers so the math would be fresh in my head, but it's okay. We can work it out. So the velocity of A as seen by E is 9/10 C. Now I've got to subtract from that the velocity of B as seen by E, but the velocity of B as seen by E is negative 7/8 C. So we end up actually minus a negative means plus a positive. So we end up actually adding them, which is exactly the same thing we did in the case of the two cars going 35 miles per hour, right? So 8 does not go into 10, so 10 is not a common denominator. 2 times 8 is 16. 3 times 8 is 24. 4 times 8 is 32. 5 times 8, however, is 40, so that's our best bet. So we're going to use 40 as our least common denominator. So that means I'm going to have to multiply 7/8 by 5 over 5, so that's going to become 35 40ths. And 9/10 I have to multiply by 4 over 4, so that's going to become 36 over 40. And obviously this gives me a difference of 70, or an addition of 71 40ths times C. So I get 71 over 40 times C for the numerator. Now in the denominator I get 1 minus. Now in this case I'm going to say 9/10 C, and then I'm going to say negative 7/8 C, and all that's divided by C squared, which luckily means this C and this C just cancel out. Okay. Now if I follow this process, I get 71 40ths C divided by, now 9/10 times 7/8. There's really no common factors in the 9 and the 8, and there's no common factors in the 10 and the 7. So I just have to multiply them out. And notice the two negative signs mean I'm going to add these quantities. But the main thing is when I multiply 9/10 times 7/8, I'm going to basically get 63 over 80. So I'm going to call 1 80 over 80. And then I'm going to say plus 63 over 80, because 7 times 9 is 63 and 10 times 8 is 80. So now what we can see is I get 80 plus 63, that's 143. So I got 71 over 40 C divided by, as I said in this case, 143 over 80, like that. Now, this means 71 over 40 times 80 over 143. You can see 80 is 2 times 40, and 40 is 1 times 40. So in this case, the 40 cancels out with the 40, and I get 142. Oh, and I left off a factor of C, so let me put that there. So I end up getting 142 over 143 C. So that's really, really, really close to C, but it's not C and it's certainly not over C. Now that's pretty impressive because we took something that was 7/8 C, that's 87.5% of C, and something that's zero point 0.9 or 90% of C, added those two together in classical physics, that would have became 71 over 40, which is almost twice C. But in this case, it still came up to just under C. And in fact, if we wanted to figure out what that was as a decimal, we'd say 142 divided by 143. And that gives me 0.993 C. So 99.3% of the speed of light. Anybody have any questions on that? I think that's pretty neat that the velocities come so close to C but don't exceed it there. I'm going to up the ante a little bit and try another one real quick. Let's imagine for a second that spacecraft A fires a photon torpedo. Its velocity is VP with respect to A is equal to C. And it's going in a positive direction, so I'll say positive C. Photons actually travel at the speed of light, so it's perfectly normal for it to be the speed of light. Now, the big principle behind special relativity is there's two of them. The first principle he said was the laws of physics are the same for all inertial observers, which means, hey, I'm trying to cut out gravity here because if you think about inertia, if you're looking at an object falling, it doesn't look like any forces are acting on it, yet it's accelerating. In that sense, it doesn't appear to be obeying the law of inertia, which says an object in motion tends to stay in its state of motion unless acted upon by some force, because you don't see a force acting on the ball falling. It is acting as if it's not inertial. So that's why he used that wording to get rid of gravity. The second principle is the speed of light is a constant independent of the motion of the source and independent of the motion of the observer, which means, like in the case of that baseball on the back of that truck, the 50 and 60 just added, but if 60 were the speed of light, then it wouldn't come up to be higher than 60. It would be really close to 60, but not 60, not above 60. So, in fact, we're now going to see what happens in this case. What I would like to know in this one is the velocity of the photon as seen by spaceship B, because spaceship B is moving towards spaceship A. Spaceship A is moving towards spaceship B at 90% of the speed of light, and it's firing this photon at the speed of light with respect to that. So you'd expect this to be like twice C or something. It's really a big deal. But according to the formula, we're going to get the velocity of the photon as seen from spaceship A plus the velocity of A as seen by B, which is what we just finished working out. And then all that will be divided by 1 plus VPA, VAB over C squared. So the velocity of P as seen by A is just plus 1C, and the velocity of A as seen by B is 142 over 143C. And then we're dividing all this by 1 plus 1C times 142 over 143C divided by C squared. I think you can probably already see what's going to happen is we're going to have to add 1 to 142 over 143. That's 143 over 143 being added to 142 over 143. So that's going to be 295 over 143C. And then the bottom, the C's cancel out, of course, but we're going to get exactly the same thing because 1 times 142 over 143 is just 142 over 143. And lo and behold, I'm adding 143 to it, so it becomes 295 over 143, and you see that the answer is just plus C. So that is the right answer for the first part and for the second part. Any questions on that? It's a really cool formula. That's the one thing that's really awesome about relativity is it's got a lot of nice little neat formulas that do interesting things like this one. Really, it's impossible to make it exceed C unless you make one of the objects exceed C, which is not really possible. So, all right, now that we have that, I'm going to press on and try to talk a little bit more about kinematics in general. So, does anyone have any questions on these two? All right, so remember that formula that I have up here. I'm going to box it off real quick for you. Remember, this is a formula that always works except when we're talking about things traveling at near the speed of light. So, unless you're within, 1 or 10% of the speed of light, let's just say 1%, then you can just use that formula. But if you're within 1% of the speed of light, then you should probably use this other formula down here. Okay. Now, let's move on to the next part. And this brings us out of the frame of reference, but I want to tell you some stuff that's going to go on here. So, we're going to talk about something called speed. So, specifically, we're going to say average speed. Now, the most helpful thing I've found about physics, and the reason why I majored in physics as opposed to like chemistry or something like that, is because the physical world and the things that I did in my life just seemed more consistent with understanding what was going on in physics. And the reason why was because early on I could see when the instructor talked about speed, I already had an idea what speed was because I knew, for instance, I'm driving a car and it has a speedometer, and that speedometer has units in it, and this units that speedometer has are miles per hour. And I'd gotten pretty proficient at understanding, basic algebra and stuff like that. And I knew that when we're talking about word problems, when we say the word per, that means divide. So miles per hour were the units for speed. That tells me that the speed must be a certain number of miles divided by a certain number of hours, or distance divided by time. So that's the way I want you to think about physics so that you're not coming up with something brand new. Rather, you're looking at something that you've been familiar with your whole life. So we'll say the average speed, which I give the symbol S with a bar over it, but some people might even use less than and greater than symbols around it. Both of those are symbols that are used for averages, by the way. If you go further in statistics, you'll find that there's very specific reasons for using bars as opposed to less than or greater than symbols, but that's not really that relevant here. Now, as I said, the speed was distance divided by time, so the average speed turns out to be exactly consistent with that, and it's distance traveled divided by time taken. Oops. Now that is the direction, the definition of average speed. It's important that you understand that. No matter what other examples or what other definitions you have for average, they're not the ones we're using. That's the difference between science and not science. Is when you're in the scientific world, we have to all agree on very specific definitions of very specific quantities. So average speed is defined to be distance traveled by divided by time taken. It's not the sum of the speeds divided by the number of speeds you added together. That would be a average, but it's not the average speed that we're talking about. Okay? So that's a common issue. Now, in addition to that, there's a quantity called velocity. And if you saw the movie Despicable Me, you know that the bad guy in the first one had the name Vector, and he said he chose that name because he did evil with direction and magnitude. He says it's a mathematical term, right? Well, he was right. That's the definition, or that's a definition of a vector quantity. A vector quantity is a quantity that has not only a magnitude, meaning a numerical size, but it also has a direction associated with it. Now, it's really nice because the thing that's not a vector is something we call a scalar. And a scalar starts with the letter S, just like the letter S starts the word speed. So that can help you remember that speed and scalar both start with an S because speed is a scalar. Similarly, velocity starts with the letter V, and vector starts with the letter V. Therefore, that'll help you remember that velocity is a vector quantity. Now, the average velocity is defined differently. Now, normally, if we're talking about some chapter other than one, then velocity could be a vector quantity and it would have, an x component, a y component, a z component, that sort of stuff. But in one dimensions, it just has one component and we call it positive if it points one direction and negative if it points the other direction. But because of that, we normally say, hey, a vector quantity has to have a little arrow over it. So we'd say the average velocity would be v with a vector over it because that's the symbol for a vector quantity, but then we'd put a bar over it like that to mean average. In this chapter, I'm not going to stick to the little arrows over the top of it, but I wanted to express that to you so you know later. And what this is defined as is as the displacement divided by time. Now, the displacement turns out to be another vector quantity. The displacement is, in fact, the difference or the change in position that you had. So when we talk about position, we're talking about on a number line, and I suggested you use the symbol X. So in this case, what we'd say is you would take X final, the final position you have, minus X initial, the initial position you have, and you divide that by T final minus T initial because T final minus T initial is a way of calculating the time taken. Does that make sense? So we can rewrite this equation a little more succinctly by saying it's delta X over delta T. And I need you to understand that change in is defined to be this Greek symbol, capital delta. So you see this capital delta. If you see this in any physical science class or any engineering class,
you're in class.
Honey.
Matthew, your sound is on, so thank you for that. Matthew? There you go. Thank you. So whenever you see the word change in, unless it explicitly tells you otherwise, it's supposed to be final minus initial. So you're going to see that this happens all through the first semester, all through the second semester, and then if you happen to take the third semester of this course, it's going to be in there. If you take statics, it's going to be in there. If you take dynamics, it's going to be in there. Strength of materials, all those different things. So it's going to be repeated over and over again. And in fact, when I say something like delta X, that means X final minus X initial. Now, throughout the semester, I use various symbols for these. So I want to show you what some of those are so it won't confuse you later. I might call that X2 minus X1, or I might call that X final minus X initial, or I might call that X final minus X zero, or I might call it just plain X to represent the final one minus X 0 like that. All of those are completely equivalent, and that'll happen from time to time. So I just want you to remember that. Now, what's the big difference between displacement and distance traveled? Well, if you consider, for instance, a number line, let's say this is our number line right here. This is 0, and this, let's say this right here is -1. This right here is 1, 2, 3. We're going to say that's in meters. I'm going to ignore the vertical axis. But if, for instance, you walked from x1 is equal to 1 meter, you walked all the way to here, which is 4, 5, 6. And then you walked back. Let's put this purple again. Sorry about that. And then you walk back 2 meters, and this position would be x final, say. Then the distance traveled is equal to 6 minus 1 would be 5 meters. So it's 5.0 meters plus 2.0 meters is equal to 7.0 meters. Does everybody understand how I got 7 meters there? Anybody have any questions on that? Okay. Looks like you don't. No question. Thank you, Colin. All right. So, yes, the total distance traveled was you went from 1 to 6. That's a distance of 5 meters. And then you came from 6 back to 4. That's a difference of 2 meters. So you went 5 meters plus 2 meters gives you 7 meters. The displacement, on the other hand, is quite a bit different. Displacement equals delta x, which equals x final minus x. In this case, I call it x initial, x1. So that's why I wrote it this way. And in fact, this is going to be 4.0 meters minus 1.0 meters, which equals 3.0 meters. See how much of a drastic difference that is between displacement and distance traveled? Now, assume this was accomplished in delta t equals 3.00 seconds. What is S bar? And what is V bar? So S bar is equal to distance traveled, which is 7.0 meters, divided by time taken, which is 3.00 seconds. 3 goes into 7 twice, and then 1's left over. So this would be 2.333. Obviously, I only have 2 sig figs there, so I'm going to underline those last 2 3's. And that's meters per second is the average speed. But the average velocity, on the other hand, is 3.0 meters divided by 3.00 seconds, which is 1.00 meters per second. So that's the big difference between average velocity and average speed. If you want to go a little further and imagine something that's not exactly one-dimensional, imagine a typical child playing t-ball. And let's imagine the kid hits the ball off the tee and immediately takes off running towards first and steps on home plate. The instant he steps on home plate, you start the timer, the stopwatch, and he runs, 60 feet to first base. And kids are all in the outfield, being chaotic like kids do when they play t-ball. They're, picking flowers, they're scratching their butt, all sorts of stuff, everything but paying attention. So the kid decides, okay, well, they don't got the ball in. The coach tells me to keep on running, so he runs the second. So now he's gone 120 feet. And then he gets there, and if he happens to be paying enough attention to the coach is telling him, hey, the kids are still out there lollygagging, so you can come to third. So he runs to third. So now he's gone 180 feet. And in fact, when he gets to third, the coach tells him, hey, man, I think you can make it home. Go for it. So he runs home. So now he's gone a distance of 240 feet. And in fact, if it took him, let's say, 12 seconds to do that, then the average speed would be 240 feet divided by 12 seconds, which would be 20 feet per second. Okay, that's pretty fast. Obviously, I made up those numbers, and that's not necessarily that big of a deal. But that's the average speed. The average displacement on the other, or excuse me, the average velocity on the other hand is because the kid ran and you started timing the instant he touched home plate, and then you stopped timing the instant he touched home plate. His displacement was zero, so the average velocity would be zero. So that's the big thing that you want to pay attention to from a conceptual standpoint. If it's straight line motion and you're not turning around and going backwards at any point in time, then it does turn out that the magnitude of the average velocity is the speed, but that is not the definition. The speed is not necessarily, again, speed is not necessarily the magnitude of velocity. It can be, and in many cases it is, but it's not necessarily. So keep that in mind. Anybody have any questions on that part? All right, so we've talked a little bit about displacement. We've talked about vector quantities and so on and so forth. We've talked about distance traveled and time elapsed. Let's look at a couple examples. I'm going to start off with example 2.1. So this is from your book, and this is where I suggested that you should be having your e-text open. This is example 2-1. Runner's average velocity. It says the position of a runner is plotted as moving along the x-axis of a coordinate system during a 3-second time interval. So 3-second time interval, that immediately makes me think delta t is equal to 3.00 seconds. The runner's position changes from x1 equals 50 meters to x2 equals 30 or 3.5 or 30.5 meters. So x1 is equal to 50.0 meters. X2 is equal to 30.5 meters, as shown in figure 2.7. What is the runner's average velocity? So they want to know V bar equals question mark. So now that I've written down all this stuff, I'm going to reread the question to make sure everybody understands. I will tell you that a good fraction of physics initially is just about learning, hey, when I read a series of sentences that make up a problem, my job is to look for all the numbers they give me and all the numbers that they've implied so I can infer exactly what those numbers are. And then I can assign those numbers a very specific symbol that represents the symbols we use in the book. So reading this question, it says the position of a runner is plotted as moving along the x-axis of a coordinate system. During a 3.00 second time interval, the runner's position changes from x1 equals 50.0 meters to x2 equals 30.5 meters as shown in figure 2.7. What is the runner's average velocity? So I try to take the time to write this out, but I'm not always going to remember to do it. But normally I try to write solution, and then I write some key information like the equation I'm going to use. In this case, I'm going to say V bar is delta X over delta T, and that should be good enough. Now I'm going to say V bar is equal to delta x over delta t, which is x2 minus x1, because delta means final minus initial, over delta t, which I've already defined to be 3.00 seconds. So this is going to be 30.5 meters minus 50.0 meters divided by 3.00 seconds. Now 50 minus 31 is 19, so this answer is negative 19.5 meters is the top, and 3.00 seconds is the bottom. Now I know, sorry about that, I know that 3 goes into 18 6 times, and then I have 1.5 seconds left over. I know 3 goes into 1.5, specifically 0.5 times. So the answer should be 6.5 negative meters per second, and that's the average velocity. And the fact that it's negative in this case told us that we're actually moving in the leftward negative direction. Anybody have any questions on that? Okay, let's look at example 2-2. I said 2-2. Sorry. I told you I'm chronically in 6th grade. That's going to continue. All right. It says distance a cyclist travels. How far can a cyclist travel in 2.4 hours along a straight road if her average velocity is 18 kilometers per hour? So what they're asking here is delta x equals question mark. What they're telling us is delta t is equal to 2.5 hours. I usually write HR. Your book's using just H. H is perfectly acceptable, but I usually write the R there. And the average velocity they give us, V bar, is equal to 18 kilometers per hour. Okay. Now, solution. What we know is V bar is equal to delta x over delta t, and we're asked for specifically delta x, so I can solve this equation for delta x. This is the way I like to do it. I tend to try to solve it symbolically and then plug the numbers in. That's the way you tend to do it as a theoretical physicist, but it's also a really helpful way because when you've done that, when you solve a equation symbolically, you've actually solved an infinity of problems. Whereas if you put the numbers in first and then solve it, you've solved exactly one problem. Okay, so it's a lot more helpful, and you can analyze the formula when you solve it accordingly, stuff like that. So in this case, I can multiply both sides of the equation by delta t, and what I'll get is delta x is equal to v bar times delta t. And when I say you can analyze it, what this tells you is, hey, if I double the amount of time, I'm going to go twice as far. Or, hey, if I triple the average velocity, I'm going to go 3 times as far. If I triple the average velocity and double the time, then I'm going to go 6 times as far. So that's the kind of stuff you can get from looking at it like this. In this case, I'm going to write 18 kilometers per hour. Notice I'm not using the SI units. Sometimes the equations we work with can work just fine. You just got to monitor the units, see what they work out to be. And if everything works out and gives you, for instance, when you're solving for a distance, gives you a distance in a unit that you like, then that's acceptable. If it gives you a distance in a unit that doesn't make any sense or in a unit that you don't want, then it's not acceptable. So in this case, I'm going to take the 18 kilometers per hour and I'm going to multiply it by 2.5 hours. So you can see that the hour here cancels out with the hour here. And as long as I'm happy with the distance traveling coming out in kilometers, then this is perfectly fine. So now I can finally say that delta x is equal to, if I multiply 2 times 18, I get 36. If I multiply 18 times zero point 0.5, I get 9. So this is actually 45 meters, kilometers is the answer. So 45, because 36 plus 9 is 45. This gives me 45 kilometers. Anybody have any questions with that? Now, I'm using a lot of words to explain mathematically what I'm doing arithmetic wise because I'm trying to avoid using calculator as much as possible. And that, makes my brain stronger, makes me stave off Alzheimer's, but it also makes it a little faster. So don't let it, make it harder for you. You just punch your stuff in your calculator. That's fine. Okay. And in fact, it would help me if you're punching your stuff in your calculator because what you're going to see is I use quick little tricks to do arithmetic. And sometimes those quick little tricks in my brain don't mesh quite well, and I'll come out with an answer that's way out in left field, like bears no resemblance to it. You'll be like, "Wow, Mr. Younger, I can't believe you figured that math out. That was really impressive." And then the next thing you know, you're like, "Man, Mr. Younger, I can't believe you screwed up that bad." So, anyways, just keep that in mind. The more you're doing calculations along with me, the better off we'll be. So please, please, please do. All right, let's look at example 2-3 now. So example 2-3, let me read it. It says, car changes speed. A car travels at a constant 50 kilometers per hour for 10 kilometers. It then speeds up to 100 kilometers per hour and is driven another 100 kilometers. What is the car's average speed for the 200-kilometer trip? So this is one of those times where they're asking for average speed, and a lot of students are sort of compelled to say, oh, 50 plus 100, then divided by 2. And that is a definition of average that we have encountered before. And it almost makes a little sense because both of them are being done over the same distance, but it turns out it's just completely wrong. Okay, so remember, we have very specific definitions in science, and we have to use those very specific definitions, not your more common definition that you're used to. So what we have here is that V1 is equal to 50 kilometers per hour for 100 kilometers, and then V2 is equal to 100 kilometers per hour for 100 kilometers. And what they want to know is V bar equals question mark. So solution, V bar equals displacement. Wait a second. They didn't say V bar, did they? They said average speed, didn't they?
I was about to ask you that. Yes.
Thank you. Nice catch. Excellent. I appreciate you at least admitting that because that's good. So yes, this is not V bar. This is S bar. So thank you for paying close enough attention to catch me on that. We're specifically asked for S bar. By the way, your book doesn't give you a symbol for speed. I use S. Some books give you symbols for speed, some books don't, but we can use it for here and just know the book doesn't really use that. So average speed. Oops, I need to write it in blue now. Or in blue now. So average speed is distance traveled divided by time taken. Now, the distance we already know. In fact, they were nice enough to give it to us, but you also figured out because he's driving 50 kilometers per hour for 100 kilometers and then 100 kilometers per hour for 100 kilometers. So clearly the distance is equal to 200 kilometers, and I'm going to assume that that's 3 sig figs. So it's 200, and all 3 digits are significant. The problem is we don't know the time. Now, this one's actually really easy. We can tell, for instance, it's going to take 2 hours at 50 kilometers per hour to go 100 kilometers, and it's going to take 1 hour to go 100 kilometers at 100 kilometers per hour. But in the event that the numbers weren't so easy, I want you to understand exactly how this is done. So I'm going to say T1 which we know from velocity equals distance divided by time, T1 or delta T1 is equal to delta X1 over V1. Now the delta X1 is 100 kilometers and the V1 is 50 kilometers per hour. And notice that when you divide 100 by 50, you clearly get 2.00. But when you divide kilometers by kilometers per hour, that becomes kilometers over 1 times hours over kilometers. So you just get hours as the unit. So remember, when you divide by a fraction, that's the same thing as multiplying by the reciprocal of the fraction. That's just, pre-algebra type stuff that we need to keep track of, even if we've been using our calculators for 7 years straight and don't remember it. Okay, you still need to be able to do that. Similarly, delta T2 would be 100 kilometers divided by 100 kilometers per hour, and that's going to give me 1.00 hours. Okay, so the total time is actually going to be 3 hours. Therefore, S bar is equal to 200 kilometers divided by 3.00 hours, and 3 goes into 180. It goes into that 60 times. And then if I want to go the extra 20, I know that 3 goes into 18 6 times. So that's 66 miles per hour. And that gets me up to 198. And then I've got 2 left over. So 2 divided by 3 is 0.66. So this is going to be 66.66 kilometers per hour. Whereas if you did that other way I suggested, where you just average the 50 and the 100, which is not acceptable in any way, you would have gotten 75 kilometers per hour. And clearly the answer is not supposed to be 75. It's 66.6 kilometers per hour. Anybody have any questions on that?
Wouldn't it have to stay at 3 sig figs?
Yes, that's why I underlined the 6. That's what I do. I've mentioned this a couple times, but you might not have heard it, and I might not have been as thorough about it in my online class. But whenever you're doing multiple calculations, it's always best to keep at least one extra digit all the way through. And the way I do that is I underline any extra digits, and then at the very end, I round it to the appropriate digit, and I know where that is because it's the digit that doesn't have an underline under it. But yes, exactly
Okay.
right. It should have been 3 sig figs. Uh, oh, wait a second. Yeah, the 50 kilometers per hour should have actually made it 2 sig figs. So that might have been what you're talking about. So that'd be 2 there. This one would be 3. That's acceptable. But that would mean that the 3 hours only has 2 sig figs. So I should call that actually 67 meters or kilometers per hour. Thanks for asking me that question. Now, we've actually gotten through the next section is section 2.3. You probably already know this, but instantaneous velocity turns out to just be the limit as delta t approaches 0 of delta x over delta t. So, and you probably know that already from calculus. So I just want to write that down so you can get started on that sort of scenario. So V instantaneous is equal to the limit as delta t approaches 0 of delta x over delta t. And you probably recognize that this is dx over dt. So we're going to be taking derivatives in this course, and the derivatives will give us functions and stuff of that sort. For instance, they give us x as a function of t is equal to at squared plus b, where a is equal to 2.10 meters per second every second, and b is equal to, in this case, I think they said 2.40. I'm looking for a specific example. 2.80, that's what it was. So this is example 2.4. So in that kind of case, for instance, you could find they specifically want us to know or want us to find what the displacement is during the time interval equals question mark for x1 is equal to 3.00 second and x2 is equal to 5.00 seconds. And then part B, they want the velocity, the average velocity during that time. So V bar equals question mark. And then C, they want to know V instantaneous equals question mark at T equal 5.00 seconds. So really what you're supposed to do, I'm just going to tell you this and then let you go because we only got 1 minute left. The displacement is found by calculating the x at t equals 5 seconds and then calculating the x at t equals 3 seconds and then doing the x at 5 seconds minus the x at 3 seconds to get the displacement. So that's how you do part A. Part B is you take that displacement that you just calculated and divide it by the time elapsed. And of course, from x1 equals 3 seconds to from t1 equals 3 seconds to t2 equals 1 second. This is supposed to be a t. That means the change in time, delta t, is in fact 2 seconds. So you're just going to divide that displacement by 2 seconds and that'd give you the average velocity. Far as instantaneous goes, V instantaneous is going to be d by dt of at squared plus b, which is clearly 2at. And of course, 2at is 2 times 2.10 meters per second times t, which is just 4.20 meters per second times t. That's the instantaneous one. So V instantaneous at 5.00 seconds is clearly going to be 5 times this. 5 times 4 is 20. 5 times 0.2 is 1. So this will be 21.0 meters per second. So I did the derivative part. I haven't done the other two parts, but you can at least look it over. I might do it at the beginning of next class or whatever, but I might just leave it. But I wanted to make sure y'all had a good start on this. When we get back, we'll start talking about acceleration, and I'll explain how that's defined, and we'll solve some more physics problems. So thanks for coming, everyone. I'm going to wait till the last person leaves before I leave, but make sure you chat me your first and last name if you haven't already.
Thank you.
Thank you. Thank you, Daniel.
Thank you. Have a good day.
You too. Appreciate that. Anybody else have any questions or anything?
Oh yeah, I just checked the homework assignments due date. It's due on the 7th. I should be fine.
For
For chapter
chapter
one.
two, for chapter one. Okay.
Yeah, it
Yeah,
states 7th.
yeah. I think I just changed that after you mentioned it to me, so it should be
Oh,
good to go.
okay.
Yep.
All right, man. Thank you.
All right. Have a good one.
All right, have a good one.
Yeah, in case y'all hadn't heard that, I did change that due date because I'd never put the homeworks for chapter one in week one module, and I should have. So just because that was my screw up, I went ahead and pushed the date back in case anybody needed it. James, do you have any questions, sir? All right, he might not be there, so I'm going to go ahead and call it a day. I do not see any chats suggesting otherwise, so have a good one, everybody. Thank you.